Hi, Year 12. Hope you had a good break and that you're ready for a fresh topic. So we're talking today about finding the gradient of curves. I can easily work out the gradient of straight lines. If I know the equation of a line, then it's easy. The gradient's just the coefficient of x. And if I know 2 points, well, we've got my good old bishop method. So how far is it in this direction? How far is it in that direction? Easy peasy. And, you know, I talked when we did this before about the slightly more formal way of approaching that by saying, okay, the gradient is the difference in the y value. So if we call this x1, y1 and this x2, y2, then we've got y2 minus y1 over x2 minus x1. And same answer as this, but that's a sort of slightly more formal way of saying it. So gradient of straight lines, no problem at all. But what about curves? Well, of course, curves are problematic because the gradient isn't the same. The gradient varies, and you know, this is a fairly basic curve, but some curves are really weird and wonderful, and their gradients vary all over the place. I mean, if we think about the trig curves, for example, they are going up and down and you know, all over the place. But maths or mathematicians have for a long time been interested in this whole idea about the gradient of curves because it's really, really useful to know at any instant how steep a line is. The gradient nearly always tells us something. For example, if this is a graph showing how something is growing, then the gradient at any point is the rate at which it's growing. And of course, rates have been very much in the news with COVID. So it's an important branch of maths. And it's a branch of maths which in the 19th century really sort of exploded. And a couple of mathematicians quite separately developed a way of working out the gradient of a curve, and they both discovered separately that it was predictable. And they discovered that if you knew the function of a curve, in almost every case you could work out its gradient at a particular point. The two mathematicians were Sir Isaac Newton, working at Cambridge, and Leibniz, a German mathematician. And in fact, there is some debate over who really should get the credit for this. But anyway, here's what they both did quite independently. So I've sort of taken a section of this curve, this little bit here, and I've enlarged it, okay? And I've picked a point on the curve here. So the x value is whatever, I'm calling it x. And because this is the y equals x squared curve, the y value is the x value squared. That's what we know. So, and the genius move that these two mathematicians did quite separately was they said, okay, if I want to know the gradient of the curve at this point. Okay, that's what we're after. We want to know the gradient of the curve at that point, and we know that that's equivalent to the gradient of the tangent at that point. So that green line is what I'm after. So they said, okay, well, we can get a pretty good approximation to that by just picking another point a little bit further along the curve. And so what they did was they called that point x plus h. They just basically said, okay, so if that's x, we'll just move along h units in the x direction. And remember the function, y equals x squared. So the y value at that point will be x plus h squared. And if you join up those 2 points, you get a line whose gradient is, well, it's not the same as this, but it's not a million miles away. It's not a bad approximation. And in the absence of any other way of doing it, it's not bad at all. So let's work out the gradient of this line here using this formula. Okay, so let me write that formula again. So we know the gradient of a straight line if we know 2 points on the line, and we do. We've got 1 point down here, and we've got one point that's a little bit further up the line, so it's h units up along the x-axis. So the gradient we know, and remember that, so we're calling that x1, y1, and this is x2, y2. So the gradient is the difference between the y values over the difference between the x values. Now before I do that, I'm just going to expand that bracket. So I'm going to grid that out. Well, in fact, I'm going to get you to grid that out. So if you would grid that out and then try and work out this formula. So you're going to do that, take away that on your numerator, and you're going to do that, take away that as the denominator. Okay? See what happens when you do that for me. Pause and have a go. So I've gridded that out, and it gave me x squared plus 2xh plus h squared. So I did that, y2, take away y1, so that's top, and on the bottom I've got x2, take away x1. And it simplifies quite nicely. I'll get to this, and some of you might have even realised you could go further because everything has got an h, so I can divide everything by h. So that becomes 2x, that becomes h, and my denominator becomes 1, so I'm not even going to bother writing it. Okay, so the gradient of this line is 2x plus h. It's not very good though, really, is it? I mean, it's not far off this, but it's not this, is it? But this was the genius thing. Can you see what these mathematicians did to make this better? What they did was they moved this point further down the line. They said, okay, let's try it there. Is that better? Well, it's better than that one. So this line is closer to the gradient we're after than the other one. Okay, let's put it here then. And eventually they said, okay, what happens if we make the point so close to the original point? So we're making h, the jump along the x-axis, so tiny that it's barely noticeable. And hopefully you can see that if my second point was so close to my first point that it was barely noticeable, then the chord that you get by joining the 2 points is pretty much identical to the gradient. So what they do is they said, okay, what's the limit of this as h goes to 0? What happens to that expression as h gets smaller? And I hope you can see that if h gets smaller, you end up with 2x. And this was a lightning moment in maths, because this was the first time that we had seen that the gradient of a curve was predictable. And it is true that for anywhere on the y equals x squared curve, anywhere on that curve, its gradient is 2 times its x value. So for anywhere on that curve, the gradient is always 2 times the x value. So if I take a point here where x is 1, say, the gradient's 2. If I take a point here where x is 2, the gradient's 4. If I take a point here where x is minus 1, the gradient is minus 2. If the function is y equals x squared, the gradient is always 2 times the x value at any point on that curve. And this process was the process that those mathematicians first used to calculate that. So I need to just adjust my notation slightly so it's set out properly. This whole idea of when you're calculating something and you're applying a limit. So we say, okay, the gradient is equal to the limit as h gets close to 0 of that calculation. And so the next stage, we're still saying, what do we get for that? And the answer is that. So we've got a function, y equals x squared, sorry. We've got a function, y equals x squared, and we've got a formula for the gradient. It's not a fixed number, is it? Because we've got a gradient that varies with a curve. So it's not like a straight line where the gradient's always the same. The gradient varies, but the formula is 2x. And this process of taking a function and working out a formula for the gradient is called differentiation. And this branch of maths, which is to do with the way that things change, is called calculus. And I'll talk a little bit more about the overarching sort of aspects of that at some point. But I'm keen that we do a little bit more differentiation and that we pick a different function. Now, you might be thinking, God dear, I mean, there's a lot of malarkey to go through. The great news is that actually this process it's predictable. There are rules that link a function with its formula for its gradient. So although we are expected to understand this is called differentiation from first principles. Actually, once we're used to it, we don't need to worry about that method. We can work out a formula for the gradient in a much, much quicker way. However, let's do it for a different one using first principles. I can't wait. Okay, so here's my function. Y equals x cubed, looks something like that. So let's enlarge a little bit of my function again. So it looks a little bit like x squared, but the key thing is that this point here, my x1 point, the y value is now x cubed. And my little point a bit further up, where the x value is, sorry, x plus h, the y value is now x plus h cubed. Now I've already done x plus h squared, I did that previously, didn't I? So actually working out x plus h cubed isn't too hard because I've just got to take x plus h squared and multiply it by another x plus h, or you might want a binomial. But anyway, my interest is, can we get the whole formula for the gradient thing sorted? So here's what I'm after. I want to know what's the limit as h tends to 0 of the formula you get for the gradient. So you're going to do h2 take away h1, sorry, you're going to do y2 take away y1 divided by x2 take away x1. Expand that first, see how far you can get this time. Bit harder, but certainly possible. Now, some of you will recognise this from Martin Lavell's presentation on the Plymouth webinar thing, and I'm sort of hoping it's a little bit clearer now, but you know, it's the same process. And he talked about, why don't you just make h equal to 0, but you can't because you end up dividing by 0, which it doesn't work. Can't divide by 0. So that's why we have this concept of saying, what happens when h gets tiny, not 0, but so tiny that we can pretty much ignore it. Anyway, let's carry on with this. I don't know how far you've got, so I want the limit as h tends to 0. So I gridded that out. I took my answer to x plus h squared and just multiplied it by another x plus h. I don't know if any of you used the binomial, but it's got that classic sort of, a cubed, a squared b, ab squared, b cubed, and the coefficients from Pascal's triangle, 1, 3, 3, 1. Anyway, whichever way you did it, hopefully you got that. So I've got that take away y1 and x2 take away x1. So on my numerator, the x cubes cancel out, so I get 3x squared h plus 3x h squared plus h cubed, and on the bottom I get h. Yet again, I can divide everything by h, so I'm saying okay. So if I divide everything by h, I can only do this because every term, there's 4 terms, aren't there? 1, 2, 3, 4. Every term's got an h in it. So that just becomes 3x squared. That becomes 3xh, and that becomes h squared. And the denominator just becomes 1, so I'm not going to bother writing it. Okay, So as h becomes so tiny, this term becomes tiny as well. So tiny I can ignore it. And a tiny, tiny, tiny number squared, again, I can ignore it. So we get 3x squared. That is the formula for the gradient of y equals x cubed. So the gradient of this line is always 3 times the x value squared. So down here, I don't know, x is -2, say, -2 squared is 4. 3 lots of that is 12. So the gradient at that point is 12, really steep. And when x is 0, 0 squared is 0, 3 times 0 is 0. So yes, we know we've got a gradient of 0 at that point. So let's add that to my list. Got my list on the previous page. Here we are. So when the function was y equals x squared, the gradient was 2x. Now it's 3x squared. Don't know if any of you can see a pattern developing maybe. I'm going to get you to do one more for me, okay? I'm not going to get you to do x to the power of 4, but I'm going to ask you to do 4x squared. Now remember, when you do 4x squared, you do x squared first, then you multiply it by 4. So see if you can go back to this point here and see if you can apply that principle to the function y equals 4x squared. I'm not going to do any sort of setup now. I'm going to leave you be to have a go at it. Come back when you've had a go. Okay, so 4x plus h squared. So I already knew what x plus h squared was. So I just did 4 lots of it, 4 lots of that, 4 lots of that, 4 lots of that. So that was my y value when x is x plus h. So I did y2 minus y1 over x2 minus x1. So the x squareds cancelled out, so I had 8xh plus 4h squared over h. H is cancelled out, so are you happy with me just doing like this time? And as h tends to 0, 4 times h will also be very, very small, so I'm just left with 8x. Okay, so we are at the point now where maybe we're starting to see some sort of pattern here between a function and the formula for its gradient. A bit of notation before we carry on. So you may remember Martin de Velde talking about notation. You know, when you come up with something new, you need to give it a name. Well, we needed, or Leibniz and Newton needed to come up with a name for this formula for the gradient. And it was for some time referred to as the gradient function, but we have a notation for it. So we've got 2 notations for functions, haven't we? Sometimes we see questions where we're given the function as a y equals function, and sometimes it's given to us as a f of x, some function of x. So if we're dealing with y equals functions, we call the formula for the gradient dy by dx, and that stands for delta y and delta x, the change in y and the change in x. That's another way of describing the gradient. The gradient is the y difference divided by the x difference. That's what that means. So 2x was the formula we got from x squared, wasn't it? So we call that dy by dx. For y equals x cubed, dy by dx is 3x squared. We did that a moment ago. And the last one we did just a second ago, dy by dx was 8x. If instead we use this notation, if the function is described like this, then we call the gradient function, the formula for the gradient, f dash of x. So that's 2x, f dash of x, 3x squared. This is just notation, where this is just me writing out the 3 we'd already found out. I'm not telling you anything new here. 8x. These are sometimes referred to as the differentials. because they are the process, the output, sorry, of differentiating, the differential. And they are a formula for the gradient. So what's the gradient on y equals x cubed? When x is 3, it's 3 squared is 9, 3 times 27. So the differential is a formula for the gradient. So in the next video, we'll look at how we can dispense with the whole differentiation by first principles thing and actually predict what dy by dx, what the differential of this is, without having to go through this process. It is on the syllabus though, so you would be expected to be able to do this. So let me just set you as your regular submission task. Can you go through differentiation by first principles with this function here? Just got to be slightly careful, because when you work out what y2 is, you've got to do 2 lots of that, take away that squared, so it would be take away all of that squared to the minus there, and then when you do that, take away that in the gradient function, again you'll have a minus both of those things. So there's some negatives in there which could cause problems, but have a go, and then on Wednesday we'll move this on. Okay, take care.